I once had a collaborator who responded. If you respond, he says, "Oh, he gets really excited, and he invites you to his dark matter social network." So he's like, "Here's your I confirm."
All right, everyone, should go ahead and get started. We're very pleased to have Michael Toomey here today from MIT. He's going to tell us a little bit about some Hubble tension, early dark energy solutions.
Sure,
so,
absolutely.
Michael, please.
Great, thank you for having me. It's great to be back at NYU. As you said, I want to tell you guys a little bit about the status of early dark energy. Anyone who pays attention to the cosmology section of Archive probably has noticed there's a lot of back and forth in terms of the discussions and the status of early dark energy, and I kind of want to give our perspective, which is in the negative, and then also talk about some interesting new constraints using sort of a rarely used parameterization of early dark energy that's actually able to significantly tighten these constraints using some MLT techniques. I guess this is what I just said in words. And specifically, there's been a lot of disagreement about this thing called prior volume effects. I'll get into that a bit later. And then a lot of what I'll be discussing today for the first part of the talk is summarized in a recent review article that I wrote with Evan McDonough, Colin Hill, Misha Ivanov, and Adrian Laposta. So anyone interested in some further details, because the thing we'll see here when I'm getting into this discussion, the details matter, right? And there's a lot of details, so they're all there. And then the last part is using this machine learning trick to use stereo-informed priors to constrain these early dark energy models.
Do people prefer it with light? If not, I'll turn it off. I mean, I don't mind doing it with light if other people prefer it.
Yeah, I don't have any like big crazy videos or anything like that, so it doesn't, either way's fine.
That's okay, really. Thanks.
So just to start off, I just want to, since this is sort of a Hubble tension type model, early dark energy, I think it's kind of important just to drive in, remind everybody what ΛCDM is, although I'm sure most of you, 99% of you, perfectly know what it is, right? ΛCDM is our standard model of cosmology. It's a 6-parameter model that's parameterized by how much dark matter you have, how much baryons, the slope, and the amplitude of the primordial power spectrum. This optical depth through ionization, theta s, and then the last one, tau reionization, and then this last parameter, theta s, which is basically just the scale of the first acoustic peak in the CMD. And these are all the things that go into ΛCDM. Oh, and I should also say, you can also rewrite these in terms of other parameters, so theta s is also H0, right? Good thing with that. There's all these assumptions we make in ΛCDM cosmology. So informed by the cosmological principle, you can write down the upper W metric, right? On large scales, the universe is isotropic homogeneous. You get the Friedmann equations. Again, I'm sure this is nothing new to anyone. But of course, the critical piece when you're thinking about Hubble tension is making sure everyone's on the same page, right? H is sort of this normalized scale factor. The expansion rates are normalized by the scale factor. So it gives you a sense of how fast the universe is expanding. And the critical piece is H0, which tells you how fast the universe is expanding today, right? I remember when I was starting out as an undergrad, when I was first hearing about the H0 problem, I was very confused about exactly what it meant. Was H0 always constant? No, it isn't. H0 is just H today. Obviously, H evolves. And again, sorry if this is obvious to everybody. But then, okay, so that's ΛCDM, right? An entire semester of cosmology in 2 slides. But now there's these tensions that we hear a lot about in the literature. What's actually going on here, right? So the Hubble tension, I'll kind of focus on that initially, but then I'll sort of say a bit about some other tensions that are relevant. And so what's going on in the Hubble tension is it's sort of a disagreement between directly measuring H0, or directly, quotation marks, using supernovae mainly. So there's sort of 2 methods to do it. There's both the Cepheid and also the tip of the red giant branch, which I'll get to a bit in another slide or two. So that's sort of directly measuring H0 in the late universe. And then there's the other side of the story, which is using early universe probes like the CMD. And what you then do is you then assume a model. So in this case, it's ΛCDM, or maybe it's some extension like early dark energy. You then extrapolate your model forward, having fit to the data, and then you can get out what your H0 value is, right? And so these values disagree. So I kind of like this plot. It sort of shows the evolution of this tension over time. So we can see around 2015 or so, the tension is starting to get above like this 3 sigma level, and it's sort of when a lot of this interest in seeing, oh, maybe there's some new physics going on that might explain this, right? And there's sort of the 2 main things people usually talk about, and of course there's a large variety of probes that people consider. But there's the direct measurements I was mentioning earlier, The big one is shoes, which is measured using this distance calibration method, where basically you measure the parallax to these Cepheid stars that have a supposedly known rate of period. You can use that information to extract distances to larger and larger scales, so supernovae, and then continue to go even further and further and measure the expansion rate to deep Hubble flow, deeper and deeper distances, measure the Hubble flow. Obviously, there's a lot of contention in the literature about that analysis. That's not what I'm here to talk about today. Of course, there's also the tip of the right giant branch calculation for H0, which is a little bit more consistent. You could probably say, although I heard there's some recent results that might be coming out soon. I haven't seen a paper yet, but disregarding that for now, just the previous results are sort of consistent with both the CND and shoes. So it doesn't really say too much, other than there could, of course, be some unaccounted for systematics in the shoes result. But then, of course, there's the H0 fit extrapolated from the CND from the Planck. And if you just take the best fit values for H0 from both of these analyses, you'll find they're sort of now sitting at about 5 sigma. So that's sort of at a significance level where you should probably take it seriously. Again, there could be systematics, but if we put that aside for now, that's sort of a picture of the H0 tension. Another sort of growing tension, although maybe it's definitely not as significant as the H0 tension, but there's also a little bit of a tension between some probes in terms of large-scale structure. So you might have heard this referenced as the S8 or the sigma 8 tension. And basically this is a tension in the inferred amplitude of the matter-power spectrum on scales of about, I think I have a line. There we go, on scales of about 8 megaparsecs. So basically Planck infers an amplitude that's about 10% higher than some other probes like DS. And so this is sort of at like the 2 to 3 sigma level, so it's definitely not as significant as H0. It could be a statistical fluke. Remains to be seen, but the important part in the story for a lot of these extensions to early dark energy is that if you have a model that is trying to increase H0, oftentimes it makes this tension worse, to the point where it's now significant and makes that model less viable. And yeah, this is just a plot sort of showing you the various measurements for S8, just to sort of give you a rough idea of how things look. So this is, of course, Planck, and then you have a selection of other measurements of S8. So you can see, the tension isn't as crazy as the H0 one, but again, you start pushing stuff around when you add in some new physics. So I think a good natural question to ask yourself is, okay, why are there tensions? Is this like something that we should expect to see? And I guess my statement would be, I guess it's not too crazy. I mean, ΛCDM is a pretty simple model. But of course, it could be the model, at least on large scales. It could be perfectly fine. These could all be systematics. But it wouldn't be crazy to think that maybe there's some like more UV completion of ΛCDM. But of course, like the coarse graining or sort of like the low res picture of what's going on, it really can't deviate that far from ΛCDM, right? ΛCDM does work remarkably well. It could be the case, there's some details we don't know. So it's not too crazy to think that now that we're in the precision cosmology era, we could run into this issue. But now sort of bringing the focus back to the specific tensions, again, sort of focusing with H0, but keeping in the back of our mind that the S8 is something we should think about as well. There are sort of two basic approaches to going about modifying H0. So there's sort of the first obvious thing that maybe you could do is play around with something in the late time universe. But oftentimes, sort of these proposals don't work out so well because, there are these phantom dark energy models, but these assume models where the equation of state is less than -1. So this like runs into issues with like null energy conditions in GR. But then again, there's these recent results with DESI that sort of might seem to suggest maybe something like this is going on. So probably doesn't work, but maybe a question mark, who knows? But I think it goes without saying that like the most straightforward and easiest type of model to implement to modify H0 is playing around with early time modifications. By early time, I mean before recombination. So quite early, so before the CMB is formed. And so this is how early dark energy works, right? And so let me just give a qualitative picture of how these type of early time modifications work, and then we'll get into the specific details of early dark energy. So let's say what do we want to do, right? Planck measures H0 to be 68 kilometers per second per megaparsec. We want to bump it up to maybe 72, 73 to be more consistent with shoes. So let's say I want to increase H0 by 10%. The effect that has is that decreases the distance to last scattering. You can just see it from here. But the problem with that is if I'm decreasing my distance to last scattering, we have this theta s parameter that's measured to incredibly high precision. So this is the angular scale of the first acoustic peak. But this is just the ratio of the sound horizon to my distance to last scattering, but you can see this is measured to like 4 decimal places, right? So this is very precisely known. So I need to do something on the other side to compensate for this. So you need to correspondingly decrease the size of the sound horizon. And the way that you can do that is you can do some energy injection before the CMB is formed, also by about 10%. And so that'll keep the effect for both cancel out. Good.
That's back.
Okay. Oh yeah, right. So you can see that if I do a 10% energy injection at about the formation of the CMB, I can get about a 10% increase in H. And I'll say this is just a very cursory overview. There's a lot of details involved, right? The CMB, the details matter, as I said earlier. But here's like a back of the envelope, background level. What do you need to do the H naught tension type solution, right, at early times? So again, roughly speaking, you need 10% of the energy density to do H naught by 10%. And then importantly, after this thing does its job, after it does its energy injection, that new component needs to redshift away as radiation or faster. Now, some other unrelated work that's not published yet, I suspect it actually should be stronger than this, but I won't get into that today. But at bare minimum, though, it needs to redshift as radiation or faster. Otherwise, there's going to have something sticking around for a long time in cosmic history. Right? If you add in something that looks like dark matter, we're going to see it, right? Because it looks like extra dark matter. Basically, 10% more dark matter, right? And if it looks like radiation, it's just going to redshift as 8 to the 4, and we don't have to worry about it. So that's a qualitative picture of the Hubble tension. So I guess before I get into this, are there any questions on any of that? So
I want to be sure
Just a quick question on the comment you just made. If you redshift, like, for example, 8 to the 3.5, does that also rule you out?
3 point, what
Like
is
if
that?
you're between matter?
Yeah, so in terms of equation of state, you want to be above, below 1/3, right? Between 1/3 and 1 would be ideal. The closer to 1, the better.
I want to be sure I understood a qualitative reference you made about early and, are you talking about modifying things really near recombination?
Yeah, so it turns out you have to be relatively close. So as it turns out, a lot of these models are usually around matter radiation equality. So redshift of 3000, obviously CMB is 1000. So depends on what you mean by close, but yeah, fairly close. And it kind of makes sense because, right, if you go too much further in redshift.
Further later or back?
Yeah, oh yeah,
earlier?
sorry. In terms of Z or A, it depends on how you think. But
Yeah.
higher redshift, right? You're
Okay,
going to be further and further out into the CMB tail, and you're less and less sensitive eventually, right? So, when you're in these redshift ranges, the CMB is fairly sensitive, right? So if you're at like redshift, let's say 25,000, and you start doing the same game, you're really going to become very insensitive to anything like this. Basically, it comes down to the sound horizon integral here is most sensitive in the few thousands of redshifts before recombination. Any other qualitative questions? Okay, so now let's get into the actual concrete. Here we go again. An actual concrete model for doing this type of job, and that's early dark energy. Although this specific thing I'm showing, I guess it wasn't proposed as a scalar field initially, but very shortly it was, which is the early dark energy proposal that was proposed by Mark Kamikowski and his grad student at the time, Tammy Carwell. And the basic idea of early dark energy, though I sort of like to explain it, is it's kind of like an EV scale inflation in a way, right? Without all the nice features that inflation gives us of getting the horizon problem and all of that, it's just the meaning being it's a scalar field at the scale EV because you need to turn on a recombination. And initially, at early times, it's stuck up its potential just due to Hubble friction. So I'm just plotting on the upper right, you can see the field evolution. And so when H becomes order m, it starts to fall down its potential. And then after that, because it's a scalar field, we can write down what its equation of state looks like. And so if I'm in early times, if I'm stuck at my potential, phi dot is 0, I'm in some slow whirl regime. My equation of state is -1, so I look like dark energy, hence the name early dark energy. But then there's a question of, okay, what happens after I fall down my potential? So this happens, so the Hubble rate is about 10 to the minus 28 eV at recombination. So basically that means if I have a scalar field, I need mass to be about that same order. So immediately this is a very, very light axion. or it doesn't have to be, but it would seem sensible that it might be something like an axion. And so typically what people have considered in the literature is using a potential of this form, 1 minus cos to some power n, and anyone who works with axions might immediately ask, why aren't you just using the 1 minus cos? Yeah, and the reason why you can't do that is this next part, is because if you calculate what the average equation of state of this field once it's oscillating at the bottom, and you plug in n equals 1 in here, you're going to see it as equation of state of 0. It looks like matter. What did I say earlier? We needed to redshift this radiator faster, right? And so basically, the choice of this potential amounts to, when you have these axions, it's coming from this instanton gas expansion, and so you're basically ignoring the first two terms, right? You're ignoring the n equals 1, the n equals 2 term, and it turns out that data tends to prefer this n equals 3 term. I could go on for a long time about how that potential is a little crazy, but that's not the point of today's talk. So if you feel a little bit off by that, you're in good company. But it suffices to say that if you plug in n equals 3, you'll see your equation of state is 1/2, right? So that's able to redshift away pretty fast. So if you have about 10%, I think it's maybe 12% there, and then early dark energy, you'll see by the time you get to the CMB, only about 2% of your energy density is in this extra field, and it doesn't screw up stuff so much that it's a big problem.
So you've taken the mass to be 0, right? The mass term and the quartic term are exactly. Identically
Yeah,
0.
that's right.
Sorry, so you don't want to talk about it, which is okay, but is there like a best model that someone has worked out that's kind of
Best model in terms of
like a natural framework for thinking?
You mean why you get a cos cubed?
Yeah.
Yeah, so Evan McDonough has a nice paper where he showed that you could technically derive a pententioner like this in string theory if you wanted to. This comes from like stacking some branes on top of each other. Definitely not an expert on that, but you could, but the takeaway is that to do so, it would be highly fine-tuned to get such a potential. So it's not like very natural to have that type of potential.
Okay, so there's not like
Yeah.
somebody claiming to have some natural.
No. Although there are extensions to this model, I did talk about one about a year and a half ago that can use a regular cosine, but it's a two-field model. So they're like, so I should say when I'm talking about early dark energy in this case, I'm specifically talking about early dark energy with this potential, right? You could of course generalize what early dark energy means by any type of situation where you're doing some energy injection. There you go, I never said that. Any type of energy injection happening before recombination, if you want to call that early dark energy, then this isn't necessarily what I'm talking about in this talk, but for this potential, the details matter, right? But yeah, any other questions? Okay, so now what happens when you confront this with data? So what I want to do here is I'm showing you, I would argue that this choice of data sets is not correct from a Bayesian perspective, but what I want to show you is sort of some of the first results. If you take the most optimistic choice of data sets and you combine them together using this early dark energy model, what does it do for you, right? So in this case, we have CMB, possibly lensing, BAO, and critically we include shoes. The reason why I say it's probably not a good idea to include shoes is if you do an analysis with and without shoes, the results disagree by more than 3 sigma. So from a Bayesian perspective, you really shouldn't be combining data sets that are discordant if you're trying to constrain these parameters. But you can see here, so sorry that the font is so small, but this is the H0 posterior. And you can see red is ΛCDM, blue is early dark energy. And you can see that in this model, you're able to get a substantial increase in H0, which seems good. Some other things that tend to change is you tend to get larger values of NS. Typically, they're pretty close to 1. So in this case, it's about 0.99. Some other critical important things, though, that you'll notice that go back to the other tension I was mentioning earlier, is that your physical dark matter density increases and you get higher values of sigma 8.
Can you tell us how much it increases the dark matter? I can't read the small print.
Yeah, dark matter is about 5%, 5 to 10%. It depends on the data set, but usually it's about 5 to 10% more. And sigma 8 is about the same. Yeah, sorry things are so slow. We don't have these chains anymore, so if I had them, I'd make better plots.
Okay.
This is like a 5-year-old plot at this point. And the reason why this data combination is interesting is despite all of those shifts to those parameters, right, all the regular ΛCDM parameters are substantially different in the early dark energy case. Despite that, if I look at the CMB, you can see there's remarkably good agreement between those two those two results I had on the last page. They only differ at the level 1%. So despite all of these changes to omega matter, to NS, and everything, you get a decently good fit. That seems good. But I mentioned that sigma 8 is a problem, right? So the CMB looks good, but if you extrapolate forward in time, right, closer to today, and you look at the matter power spectrum, you'll see that you actually get a roughly 10% increase in the power spectrum, which corresponds to roughly, again, depending on the specific data set, about a 5 to 10% increase in sigma 8 or SA, depending on what you want to use. And that's enough to push you into the regime where, okay, it was like 2 to 3 sigma in ΛCDM for large scale structure tension. Now we're at like 5 to 6 sigma, again, depending on the data set. And this is something that was pointed out a few years ago by myself and collaborators and some other people as well. And so now let's do something that, yeah.
Could you give a quick, like, intuitive explanation for why ED touches matter clustering and why it affects sigma 8?
Why SA needs to go a little bit higher?
Yeah.
Yeah, so in a few slides I'll be getting into the physics of actually what's going on, yeah. So if I don't answer my question, then feel free to ask again. But now, something that surprisingly wasn't done in some of the first analyses, and this is something that myself, Colin, Evan McDonough, and Stefan Alexander did in our first paper on this, is if you just take early dark energy and you just fit it to Planck by itself, what does that look like? Well, if you do that run, and critically I should say what we do here is we take, as far as the model, remember for the model we had sort of two different ways that you can parameterize your model in terms of fitting. So you can either choose your priors over the mass and decay constant for the axion. There's also the initial misalignment angle. But that would be the same for both choices of parameterization. But you can also do a choice where you go over FEDE, so the maximum fraction of that early dark energy. Remember, it's usually about 10% for doing something like H0. And then log 10 ZC, or just ZC, which is the redshift where that peak is. And we'll see a bit more about that later. But if you do your scan over those parameters and you take uninformative priors on that, just flat priors, you'll see that actually just at the level of Planck, there is no preference for early dark energy, right? So maybe you could argue if you start throwing in some other data sets, maybe it'll start to be sensitive, maybe the CMB is unhappy with it a little bit. But I should say, I forgot I had this. So that was sort of an old result. In the last few months, we actually updated this analysis. Planck included some new likelihoods recently. So we reran all of these things with the new likelihoods, so there's 3 other likelihoods. And they're all consistent with not particularly liking early dark energy. So here's FED here. You can see we're all up against FED equals 0. And again, this is just CMB for now. But if you look at the posteriors with the CMB, you'll see we have some degeneracies. In particular, there's some degeneracies between these new early dark energy parameters and some of the regular ΛCDM parameters, notably H0, omega dark matter. And so you might be a little bit concerned that we have these degeneracies. So the obvious way to break it, because we're dealing with dark matter sigma 8, H0, is you can start to throw in some large scale structure data. So I can throw in some weak lensing, BAO data, and you're able to roughly break those degeneracies. But you see that you still don't have presence for early dark energy anymore, it makes it worse. And then if you're looking over here at S8, it's roughly, it's basically including the omega dark matter, forces you to lower FEDE. And I think I explain in the next slide or two why that's the case. I think it's the slide after this. So in addition to using the weak lensing, you can also use BOSS galaxy survey data using EFT of large scale structure in your analysis. And so again, we see we don't have this favorability. FEDE is highly constrained. And then, okay, so here's a question. Now what's going on? So I think this goes back to what you were asking earlier. What's causing this to happen? And the main thing that's going on is it's because of the integrated Sachs-Wolf effect. There's also a regular Sachs-Wolf effect piece as well. But the main one you can think about causing this is the integrated Sachs-Wolf effect. And basically what's happening is that because you have an extra component around recombination that doesn't look like dark matter, you have this extra piece, equation to state 1/2, it's about maybe 5% to 2% depending on the fit. That adds some extra power to the CMB. So we can look at the temperature power spectrum here. In black, this is just regular ΛCDM. Now keep all the parameters fixed, add in early dark energy at 10%, that gives you the red curve. And now in addition to that last step, now add about 10% more dark matter, no 12%, sorry, and then that will drive it back down. So the reason why early dark energy is not favored is because to maintain your good fit to the CMB, you have to add about 10% more dark matter. So you can qualitatively now imagine I'm starting at the CMB with sort of the same perturbations, but now I have 10% more dark matter that I'm now going to have to evolve forward in time, and that's going to be faced with large scale structure data, and that's what drives the preference for early dark energy down. Because again, you get a roughly 10% enhancement in the power spectrum. Oh, here's just a zoomed in version. So then, okay, I've just given these results. Only one of those results was new, the choice with new likelihood. So people are probably asking, okay, why am I here today? Why didn't I give this talk a few years ago? Well, I did. It's because there's been a large debate in the literature, and tons and tons and tons of papers on early dark energy have come out in the last few years. But there's just a selection of them. There's a big disagreement about prior volume effects, about driving these results. And the basic statement of what these prior volume effects, what people argue is that because I can take the FEDE, again, the maximum fraction of this field, I can take that limit to 0 and that becomes degenerate with ΛCDM. So they argue that there's now this large swath of parameter space that sort of effectively increased the volume, and that when I marginalize over that space and I go to constrain something like FEDE, I'm artificially disfavoring the higher FEDE regions because my sampler has spent more time down here than it has up here, just because the parameter space is so much larger in this regime. And the main way that people have gone about making this argument, specifically calculating something called profile likelihoods. And basically what they do is you can take the data, so in this particular case it's using Planck plus BOSS. So BOSS is a large scale structure probe, this is using EFT of large scale structure. So similar to a result I showed earlier, and what you can do is you can maximize the likelihood, but only finding what the maximum likelihood points while keeping as a function of FEDE. So basically what this plot is showing you is that there's a region in the early dark energy parameter space that actually has lower chi-squared by about 4, versus in this regime where this is ΛCDM. But the problem with that is, right, just because your chi-squared value is lower doesn't mean your model's a better fit, right? And notice in this particular case, right, it's only delta, right, delta chi-squared is order 4. But early dark energy has 3 extra parameters, right? So you can imagine I now have a model with 20 new parameters that in the limit looks like ΛCDM, I could have a delta chi-squared of 20, right? Provided that I don't have any sensitivity to that model, right? This is an important fact. If there was actually early dark energy, I should expect this to be a lot more significant, right? It shouldn't just be 3 or 4 in terms of delta chi-squared. So there's a few arguments that you can go about actually looking at this in detail. And again, sorry if these are very good details, but I mean, I think this is an important model to consider, right? It's a big problem, and the details matter, and so there's a bunch of tests you can do. And I think the simplest one you can do is instead of using this FEDE and ZC choice, you can sample over the particle physics priors directly. And some people might question, why wasn't that done already, right? The main reason is it took a month on the CCA on 400 cores to just do the Planck analysis by sampling those parameters. I'll say a little bit later exactly why that's the case. But you can see if you take that choice of priors, you're way down here in terms of the allowed fraction of FED.
Sorry, I'm not quite following. What are the parameters you're sampling specifically?
Yeah, sorry. So remember that we have an axion, right? And sort of the axion is a scalar field and has a potential, right? So I can write its potential like this. 1 minus cos theta. In this case, we're using the n equals 3 potential. And so there's 3 parameters in early dark energy. So here's 1, 2, and then 3. Instead of, this is the particle physics theory parameters, but I can equivalently sample over these other parameters, FEDE and ZC, which basically you find just by doing a shooting algorithm in class. So you can map these particle physics parameters onto these effective parameters. Then remember that FEDE is just the maximum of the energy density in that field, and then ZC is just where that happens. So you can sample over both. Fundamentally in class.
So wait, the shape is going to depend on how you sample in those other parameters. So
The shape of, you mean the contours? You mean?
I may not be following. You're going a little fast for my
Oh,
brain.
my apologies.
But
yeah.
I think you're showing us the distribution of values of these parameters.
So, this is the evolution of the energy density as a function of redshift, right? This isn't like a.
For different choices of the parameters.
No, this is if I fix, let's say I've chosen a
Oh, just
fixed
some
mass.
representative value.
Yeah, if I've chosen, say, mass 10 to the minus 27,
Oh, okay.
decay constant about the Planck scale, theta of, say, pi, and I plug those numbers in, I can calculate what the maximum fraction of the energy density is and what redshift that happens at. And I can like map between those two. I'll have a little bit later, I'll have an analytical expression.
Sorry, I think you were trying to tell us that this was the distribution that you were getting. Okay.
No, no.
Yeah, just a follow-up question. So you have 3 parameters, but and you said theta is pi typically? Or?
Yeah, usually theta needs to be high. It has to do with the sound speed of the perturbations, is why you typically have to have pi, but.
So a simpler model that you could have is lambda phi to the 4th, and then you just have one parameter and one.
Yeah, that's a good
misalignment
question, but that actually doesn't work.
That does not.
Yeah, and this has to do because of the perturbation sound speed. So there's some work by Lisa Randall about 5 years ago, these rock and roll Hubble tension papers, where they look at phi 4 and phi 6 papers, and those are ruled out. And again, it has to do with the details of the scalar perturbations.
Sorry, I'm still confused about this. So why doesn't this give you the same constraints that you were seeing when you were just doing?
It'll probably make a little bit sense in a few slides. I'll do a transition to doing a slightly new thing, and then it'll be a lot clearer, I promise, like when we get there. So maybe if you could hold with me for like maybe 5 more slides, I think that'll make sense. Because what I'll be doing in that last part of the talk is I'll be using, instead of using a prior on these guys, which most people have done for computational reasons, it only takes a day to sample these. It takes a month to sample these for Planck, right? I'll be actually using an ML trick to actually sample those.
Okay.
And then I'll explain some of those details. Okay, but now going back to like testing for this prior volume effect, again, the argument is that because as this fraction goes to 0, I become degenerate with ΛCDM, just purely indistinguishable. Another thing you could consider doing is doing an analysis where I artificially cut my prior at some fraction away from 0, right? So in this particular case, you can imagine running at say 4%. So you allow values for FEDE to take on values 4% all the way up to 1. And if you run that analysis, you find that you're right up against the prior, right? So presumably, if your argument was that if I go on the limit where FED equals 0, this prior volume space becomes so large that when I marginalize over all the other parameters, I artificially weigh things down. That argument doesn't hold here anymore because I've now artificially excluded that region. And you can see I'm right up against the boundary of the prior, right? If early dark energy really existed, I'd expect now to have a little posterior right here, centered around, say, 10%, but we don't see that. But I think the real nice detailed thing that shows you that everything makes sense and is consistent is if instead of looking at the profile likelihood, which is a frequentist metric, again, this is where you just basically calculate precisely what the maximum value of the likelihood is as a function of this parameter. If instead you calculate what the mean likelihood is, and the way that you do this is you look at your MCMC chains, you know what the likelihood is for each point, you bin everything in terms of FEDE, and then you calculate what the mean likelihood is. And the reason why this is nice is if we see, let me make sure I got solid and dashed right. Okay, so solid here is our posterior, so this is basically everything I was showing on the other plots. But if I plot instead also the mean likelihood, which is this dashed line, you can see both the likelihood and the posterior are both monotonically decreasing functions, right? So what does that tell us? Remember, the posterior is our prior times our likelihood, right? So we can see that this result, this posterior, is driven not by the prior, but by the likelihood. And I have it here for 2 different data sets, Planck plus Boss, and then Planck plus Boss with SA. So for me, this is very convincing. Basically, the reason why you don't see a bump here, right? We saw the other plot that was the frequentist plot with the profile, and we saw that delta chi-squared was about delta chi-squared is -4. The reason why we don't see a bump there is because there's a very small region of parameter space that has a very slight preference, very small, for non-zero FEDE, but the larger swath of parameter space does not. And you can test this with this mean likelihood, and I should also say the mean likelihood suffers from no prior volume effects. So it's like the volume of the space doesn't affect that curve. So this is like a very robust result. I guess, said this earlier when I first showed this plot, is that even the frequentist interpretation of this plot is also that ΛCDM is favored. Again, being delta chi-squared is only 4 in this case, but I have a 3-parameter model. Right? Okay, so any questions on that part? Hopefully, I've convinced people, I mean, there's 4 nice tests there. If you don't believe one, hopefully you believed another, that these early dark energy results, the reason why you don't see anything is precisely because the data has the constraining power to say that it isn't there. Right? It's driven early by the likelihood and not by the prior.
What's AIC score?
The alkaline information criterion. So this is a way that you can, account for, how many degrees of freedom and how many model parameters. Yeah, if you use that in this case, it isn't very. Okay. So now let's transition into a new result. And so hopefully now I'll start to answer your question from earlier. Sort of when you do these analyses, again, you take these priors on FED and ZC, right? And typically what you do is we don't really have a place to go to for some intuition about what they are, right? There isn't a previous experiment that's constrained early dark energy. So what you do is you just do the typical Bayesian thing. You take some uninformed uniform priors on FED and ZC. But the problem is those parameters, you have to map them onto these particle physics priors, and it's not necessarily clear whether those priors are physical or not, right? And so in principle, if we were able to find a way to sample those priors and constrain using the particle physics parameters, we could probably put a lot more stringent and more accurate constraint on the model. But again, previously this was computationally inefficient to do. So what I'm going to be presenting here is a way that actually using a type of machine learning, specifically normalizing flows, as a way to circumvent this problem. So what I'm going to do is sort of, along the way, do a little introduction to machine learning, because I know maybe some of this audience might not necessarily be familiar. Guess I'll have to be a little bit quick. Sorry if I burped, I ate very quickly. Well, I'm sorry. So just a quick synopsis, what's machine learning? Machine learning is just a branch of computer science that deals with basically algorithms that instead of you writing down an algorithm to get some outcome, the algorithms learn from the data to solve some problem, right? You're probably familiar with neural networks. There's of course ChatGPT now. Yeah, I guess this is what I already said. So there's traditional algorithms where I have some data, I write some algorithm. Let's say I'm trying to fit some power spectrum with some likelihood, right? I can write down that algorithm, I take that data in, and I get some output. But what machine learning does instead is it turns that apparatus on its head and it says, okay, I've taken some data, I observe a bunch of images of, say, cats and dogs, and I want to learn some algorithm that is able to classify between them. Now imagine trying to do that by hand. It'd be very hard to do, right? I challenge anybody to do that, very hard. Of course, there are a large variety of machine learning architectures. I'm not going to bother naming all of them, but there's a bunch of them. And each one of them is sort of well-suited to different tasks, right? So it's very important if you want to address a problem, you find a well-suited architecture. And of course the question is, okay, why is machine learning useful? Of course, sometimes I feel people kind of overuse them to do very simple things just to do some machine learning, and that's not particularly interesting. But they can be very useful in the sense that they're very good at solving very high-dimensional problems, like the cat versus dog example I gave earlier. Again, hard to do by hand. They're very good at speeding up calculations. Let's say you have a bunch of data of simulations and you don't want to waste, a bunch of trees, killing a bunch of trees using cluster time. You could imagine training ML algorithms to speed things up. They're also able to actively update themselves. And importantly, we'll see this later, is they're able to generate new patterns or generate new features from the algorithm after being trained on some data, trained on some distribution. You can then sample from that distribution after having trained it. I guess I did have one animation. But of course, there are some downsides to ML, right? And the big thing is that it's sort of a black box, right? So let's imagine the cat versus dog algorithm, right? It's not exactly clear what's going on, although you can sometimes open up the architectures and sort of see bits that look like ears and noses and whatnot. So you can sort of gain some intuition, but it's still kind of a black box. It's not entirely clear what it's doing. So that's kind of a big downside of machine learning. But there are some machine learning architectures, and I would pose that this normalizing flow one is one of them, that are able to sort of be less of a black box. Still a little black, but a lot clearer, maybe a gray box. I'll just skip this slide for time. So straight into these normalizing flows. So what are normalizing flows? Normalizing flows are a type of generative machine learning, or it's a type of generative machine learning architecture. And basically what they're very good at is learning complex probability distributions. And so basically, specifically what you do with these normalizing flows is you're able to map between a very simple distribution, say a Gaussian, that's why they're called normalizing flows, normal distribution, to a much higher dimensional complex distribution, right? And specifically, you do it in such a way that you learn a bijection, so all probability is conserved. You don't need to worry about anything bad going on. I won't have too much time to go into the details about normalizing flows, but I'd be happy to answer questions afterwards. But I'll just flash this up for a second. This is some of the details, of course. But the premise of it is basically just the change of variables formula. So you can imagine that I have some probability distribution. I wanted to change to some other variable. This is just the function you would write down. But in this case, again, what we want to do is let's imagine this p hat of theta as some complex distribution that we want to learn. And then this pi mu is some Gaussian. It's a very simple distribution. I know how to calculate all these probabilities analytically. I know what its Jacobian and all of these nice things look like. They're very easy to deal with. And then I have this function f that's able to learn some transformation between these two spaces. And as it will turn out is we actually end up using a neural network. Again, don't have the time to get into the details, but the rough picture being these normalizing flows are an easy way to sample very complex distributions, and you're able to fit them specifically to your data. And the way that you do that is you basically take your data and you try to minimize the log likelihood of that distribution. Basically, you're finding the mapping between this high-dimensional complex space to your simple Gaussians by feeding it the data. And then once you've minimized this, or sorry, maximized this log probability, you'll find that you basically can converge to the exact likelihood. With a caveat, there should be a little asterisk mark there, I guess there is one there, is that if you haven't properly sampled the space, it isn't quite exact, but you can do some tests, some just robust tests, like simulate a bunch of Gaussians in some dimensional space and then test that you're properly getting back what you put in. Or you can imagine inverting, taking samples that you generate that are expensive, feed them backwards to the architecture, to the base distribution, and checking that that distribution is properly Gaussian. So there's some tests you can do. But qualitatively speaking, what's happening with the normalizing flows is it's just a very cheap and easy way to learn how to sample these complex distributions. So what is that complex distribution for us, right? Well, specifically what that complex distribution in this case is this mapping between these particle physics parameters and this early dark energy parameterization plus all of the other ΛCDM parameters, right? That's an important thing, right? You could imagine binning, you could basically simulate with class a bunch of different times all these parameters. I could calculate what FEDE is, what ZC is, and you can imagine binning those values, fitting a curve, and getting some like pseudo prior for these parameters. But these all depend on cosmology. So I'm able to learn with these normalizing flows a conditional distribution. So I can take my MCMC chains. I guess I'm getting a little bit ahead of myself, but I'm able to learn the conditional distribution. Right? And importantly, of course, so remember I said earlier people usually use this FED and ZC, and they use flat uninformative priors. That's because, again, that's what you do as a Bayesian. You don't have any information about that already. But on the particle physics parameters, there are some thinking, there are some priors about how they should be distributed. If you look at some of the stringing literature, you'll find that both the mass and the decay constant are typically log distributed. Also, they're typically, you wouldn't want to have any field excursions, and also you don't want the decay constant to be too large. Again, maybe there's some asterisk marks, maybe some people, some of the theorists don't agree with some of these things. Well, let's say you take all of these as a prior. But then now I want to say a bit about, I guess sort of related to what you were asking before, is why exactly is sampling over this parameterization more difficult than this effective parameterization? And so a way that you can start to see it is just by taking a slow roll approximation, right? We have a scalar field, and I can just do some approximations so I can see how ZC and FED analytically depend on the mass and the decay constant. Also theta I, which is just phi I over f. Don't worry too much about the details of the equation. Suffice it to say they're simple enough where you can write something down and then you can make a nice plot like this. And you can sort of see for different values of FEDE, for fixed ZC on this plot, you can see that it sort of falls in a narrow band. So you can see we're ranging from like 0.01 to FED of 0.15. And you can see they're in a pretty narrow band in terms of the decay constant, theta I, and then here's the mass and theta I, again, just using that equation on the last slide to map from FED-ZC to the particle physics parameters. And so you can imagine that if I'm taking now uniform samples in the particle physics parameters, right, F and M, there's a small band, right, of non-zero FEDE. It's all zero out here. And this is sort of where these people who are concerned about prior volume effects, this is sort of where they're concerned, right, as we have these regions. And I sort of already showed you from the profile, the frequentist profile likelihood, there's a small region that has a little bit of preference. So when I do my MCMC, I'm dropping all my chains down in this parameter space Some of them are kind of want to hang out there, right? But eventually it'll reach thermal equilibrium. Your Gell-Riemann statistic will be good enough where you can say that everything's converged. And it turns out, anyway, they don't like that region, right?
Michael, how can I see there's just a small peripheral region? It's the difference between the blue and the red?
It's just that you can see that if I plug in, like usually these early dark energy models are like order 10% is what you need. And you can see that if I go from say 0.5 to 0.15, that's a very small band in terms of FED and ZC in log space.
Between the green and the blue.
Yeah, that's non-zero, right? And this is the region that has a little bit of preference, a slightly smaller delta chi squared. So some chains do get propped down here, but because they don't look like the distribution for the other guys that ended up down here, it takes longer for the chains to converge, right? But eventually, if you run them for a month at the CCN 400 cores, they do, right? But it just takes a long time. But in principle, it'd be basically impossible to do this with other likelihoods, right? Imagine doing this for large-scale structure, or some of these in other analyses with Planck, it would take a very long time, right? And so the basic idea is now using these normalizing flows to learn this mapping in a cheap way. And we'll do this using something called importance resampling. I'll get to that in a bit. But just a bit about what we can say about the priors. I alluded to this earlier. So one sort of informative prior you can take on the particle physics parameters. This is what we're going to need to train the normalizing flow. You can go to the axion-like gravity conjecture, and it basically tells you that the decay constant should be sub-Planckian. But here's an interesting plot on the right-hand side I'd like to show, is that if you assume uniform priors on FED and ZC, and you map them into the particle physics priors, and you look at their distribution, the interesting thing is if we look at the decay constant, basically almost half the prior is above the Planck scale. So in a way, when you're assuming uniform priors on FEDE, you're sort of assuming, at least from the perspective of the axion-like gravity conjecture, and some may say that's wrong and that's fine, but if you take that as your prior, that is unphysical in that sense, right?
So here, F is some fundamental, because there are ways of like simply model building it where to get some effective F that's like 10 M Planck or 100.
Yeah, of course, and you could make that argument. I'm just saying, if you, and I will say, these priors, if you, let's say you loosen the prior on it being at the Planck scale, the most critical thing, the thing that drives the most of the results I'll show in a bit, is actually that they're log distributed. That has the most power in terms of making what the informed prior is. But that's a good point. I mean, of course, you could say this isn't right, but I could still run with the other arguments that it's log scaled in both mass and decay constant. I think that's fairly robust from like a stringy axion perspective. And it turns out later that's mostly what drives the result, less so the decay constant. But no, that's a very good point. I can then take that axion-like gravity conjecture, and again, for this analysis, we're going to assume that. I can rewrite it in this nice way where I can sort of see how the early dark energy parameterization depends on the particle physics parameters. And you'll see that if I assume C is some constant, that I guess there's a lot of debate in the literature about exactly what value it is, but it should be like order 1. So if you sort of take that at face value, it says in the early dark energy case, for an axion of mass 10 to the minus 27 eV, that your decay constant should be like 0.01 M Planck, which that's pretty strong considering that the typical best fit values for these decay constants in early dark energy models is basically at the Planck scale. But what we end up doing in this work is we assume like a very weak axion-like gravity conjecture where we assume less than Planck. But again, you could change that prior if you don't like it, right? You could just let it be as high as you want, and then just use the log MF. But so that's the priors that we do use. We train our normalizing flow using 6 flow transformations, which we model with these masked autoregressive flows. Don't worry about the details, but if you know what they are, that's what we use. And then all we have to do is we just have to minimize the log likelihood using just standard machine learning technique of stochastic gradient descent. A little cut off there, but you can see we have decent convergence after a long time of training. But again, well, I say a long time, but it only takes 10 minutes to train. And then what we can do is, remember I mentioned before that you could just naively bin things, so you could sort of come up with a very cheap prior by just fitting some curve to this posterior, but it's not, right? It's just binning this mapping between uniform samples on the particle physics parameters. But if you actually train your normalizing flow, you can extract those distributions conditioned on some cosmology. So in this case, it's just conditioned on Planck cosmology, the other ΛCDM parameters, and you can see the distributions don't look the same. They're kind of similar, but they're not the same. And you can especially see here, right? theta I looks pretty different. And it makes sense that if you choose Planck, that theta I would be a little bit more flat, because when theta I is high, FEDE goes up. There's a correlation. Okay. Nice. And so, okay, what can you do now? So, okay, I know the mapping between the particle physics parameters and now the effective parameters. So you might say, okay, it doesn't make a lot of sense to learn this mapping since I already know them theoretically. But again, remember the point was to learn the dependence on the cosmology and not to use those prior to then start doing runs with. Since the model is already strongly constrained with the effective parameters, it's perfectly sensible to just do importance resampling. So I can update the prior and post. I have all the chains. I can just update the prior using my normalizing flow, and I can then improve my constraints. So here's a case where I'm comparing a bunch of different contours. Sorry if there's too many. Black is like the very optimistic, one of the first results for early dark energy. Said, oh, this solves the Hubble tension. You can see in red, let's see, that's just ΛCDM on H0. Maybe let's focus here on FEDE. So red is, did I make the colors wrong? Red. The red should be early dark energy. No, sorry. Oh, okay. Oh, yeah, this is early dark energy with just Planck with uniform priors, so the standard analysis. And then green is using this normalizing flow. So you can see that the favorability or the allowed early dark energy drops down quite a bit. Yeah, I guess I didn't have the colors off, I just can't read. And so that was in terms of those effective cosmology parameters. And then just here's a quick look. So again, H0 S8, but now with the particle physics parameters. And one thing that you'll notice when you use this neural density estimator, so this is the field distance that it traverses from initial to the end. And you can see, so there's also the distance conjecture you might be concerned about in terms of a theory perspective. And you can see that in this case, we're definitely way away from delta M Planck of about the Planck scale, or delta 5 around the Planck scale. So that's all good. And then, okay, we're coming right to the end. And so I think this is sort of like the biggest result so far, is this is the strongest constraint on early dark energy that I know of. And so what we're doing here is if you take Boss plus Planck, and you assume all the standard priors and everything, that's the black curves. But now if you use our normalizing flow, you can see that we get a substantially stronger constraint on FEDE to the point where it's less than 2% at 95% confidence. So that's basically in the regime where you can probably start to say that this model is basically ruled out. Because you could probably start to reasonably alter H0 at about 5 to 6%, right? That's enough to start increasing it enough where it's probably within like 2 sigma. But at this level, you're way too far away to really do anything appreciable. And then the great thing about using these normalizing flows, I guess just a little advertisement for all the people who put together these packages. This is how easy it is to use it once you've trained it, right? This is 5 lines of code. Takes like 2 minutes to run, right? Remember, training took 10 minutes, but like 2 minutes to run this guy after it's been trained. It's very easy to integrate into like using Cobaya or Monty Python. Okay, so now just to conclude, I would say the canonical n=3 potential axion-like early dark energy models are strongly disfavored by current data. I personally would say it's already ruled out. Importantly though, one of the big points of this talk is to point out that this argument that prior volume effects are swaying these results, I think that really isn't supported. Give 4 concrete examples that sort of say why that isn't the case. And precisely why you don't see anything is because the CMB and large-scale structure data are so constrained. All of that said, I think EDE-like models are still very promising to look at and still consider, but the specific model that, again, has a lot of attention, probably a paper every single day, maybe every other day comes out on this. Maybe not so much recently, but there's a fair amount of these papers. And then another thing just about the end is I think the integration of like these more concrete machine learning architectures like normalizing flows, I think could be very promising. Given that they're a little bit less of a black box, it's very concrete what they're learning. They're learning these complex probability distributions, and they're easy to integrate into a standard Bayesian inference pipeline. And I guess I'll conclude on that. Thank you.
Question, Michael?
Do you know how things change if you instead of boson? uniform prior on F and some log prior on M?
Yeah, so we've done that analysis as well. I don't think I have a plot in this paper, but it still increases the constraint substantially. Yeah, we've tried all combinations, log on F, linear on F, log on M, linear on M, and all combinations thereof. Each case is always more constraining than just uniform, just the regular uniform priors.
See, and then is there, I'm trying to see, is there one way of like describing everything without ever talking about FED or ZC? Because can't you write like all the Boltzmann equations just in terms of the
Yes,
fundamental
of course you can. And the reason why you can't, I mean, in principle you can do it, and it's only ever been done once to my knowledge, right? This is the paper that myself, Colin Hill did a long time ago with Evan Dunn and Stefan. The problem is it just takes too long, right? So that's the big take home of that normalizing flow at the end, is that it's a cheap way to do an analysis, including large scale structure, without waiting an entire year for this run to finish. So you're absolutely right, you can definitely do this run, but just the way that the parameterization works is it's very hard to sample it efficiently. So that's why this is an interesting hack to try to get around that problem. Is it ideal? No, but is it better than running a thing for a year on 400 cores? I would say it's probably better and more responsible to do an analysis that way.
So for the final bound you showed, assuming, I think you said the standard theory priors that you showed earlier, you get like 2%, 2.5% or something like that.
Yeah, you mean this,
DE. Sorry, can you remind me, does this assume that C is less than 1, or did you allow it, like, the fraction of F greater than M plane? Did you allow that?
Oh yeah, so in this particular case, this does have the strong, or sorry, well I call it the weak axion gravity conjecture bound, because we just restrict it below the Planck scale.
Right.
But yeah, technically it would be closer to 1%, but you're saying if we remove that.
If you allow it to be like 10 or 100.
We have done that, so we've done that run, and so this is closer to say 3%, if you remove that.
It still doesn't change that much.
No, but the critical thing is if you just do the mass and the K constant log scale, it helps the constraint significantly. So, right. So yeah, you could change your prior in that sense, right? Which is fine.
Yeah.
Good. For this comparison here, did you run both chains until they both converge, or did you set like a maximum step number?
Yeah, so in this particular case, to make sure I got the colors right, the black curve, so that was run until they converged, right? Gelman-Riemann of, I forget what it was, but it's probably like 0.01 or something like that, whatever it was. But then importantly, the red chain, that was not run again. I used the same chains, but I did importance resampling and post-processing using the black MCMC change. And you might be concerned, is that valid? But the reason why it's kosher here is because, right, in both cases, right, the results aren't dramatically different, right? If it was a case where like, oh, it was detected at 10% and now it's down here, then I think you have reason to be concerned. The constraints just got a little bit tighter. That area is sufficiently sampled where we can trust using importance resampling. Because these things run for a long time. Even with the effective parameterization sampling, it takes a long time compared to regular ΛCDM. So very well sampled. You have a question as well?
Well, it's a really very nice analysis, I like that a lot.
Oh, thank you.
Where does it leave you thinking about?
Oh, where does it leave me? Yeah, so I mean, I spend my time, I guess I sort of alluded to it here, thinking about like other EDE-like models. I think it's still very promising, but I think my intuition is sort of maybe the statement that radiation are faster. If you want to do, there's other ways you could do this, right? You don't necessarily have to do energy injection. You could play with like the sound speed, the photon baryon plasma. You could maybe change when recombination happens. So there's some models that do that. But if you want to do the energy injection, if you actually go into the details of like the integrated Sachs-Wolf effect and even contributions for the ordinary Sachs-Wolf effect, my gut feeling is that I think the statement needs to be a little bit stronger than faster than radiation. I think the closer you are to acting like kination during this transition, I think the better you're going to be. Just because, again, you get excess power.
You are to acting like what I just didn't hear.
Oh, kination, like a fast roll scalar, right? Equation of state of 1. Right. So I think maybe the statement would be, roughly speaking, and this is something I'm thinking about now, is maybe like some rough statement about where you'd have to be, but maybe like faster than like 1/2, W less greater than 1/2, instead of 1/3, which is like radiation. just because of, again, the Sachs-Wolf, integrated Sachs-Wolf piece seems to spoil things in terms of needing to add more dark matter. So if you could just kill off that energy density like that, because 1/8 of 6 is going to be pretty fast if you can get a fast roll scalar, and I do have a model that can do that. I talked about it here about a year and a half ago. We're only just now doing the data analysis. But I think models like that are promising as far as doing energy injecting type early dark energy models. So yeah.
No last questions. Thank Michael.